Hello student, how are you? I hope you all are good. So in this lecture, we are going to see the problem based on bar elements. So see, this is the given problem. There is a bar element. See, this is the bar element in which they have given F2 force at this second point, right? Second node. There are three nodes here, first node, second node, and third node. If you will see at the second node, why we have taken the second node, there are two reasons to select the second node. First reason is the force is acting at that point. The second reason is the area is changing. There is sudden change in the area. So we have to select that as a node. And first node and the third node is because of they are at the end. So at the ends, we have to select the nodes. So here F2 force is given. So once we have selected the three nodes, so obviously this is the problem of two element bar element, right? There are two elements, element 1 and element 2. Element 1 is this one. This is your element 1. Node number in between node number 1 and 2. In between node number 2 and 3, there is element number 2. And the remaining details are given that length L1 is 300 mm, L2 is 400 mm, area of first element is given, Young's modulus of first element is given. Similarly, the area of second element as well as Young's modulus of second element is given. I have taken this. Let us take the force at the first node is F1 and the displacement is U1. Similarly, at 2, U2 is the displacement, F2 is the force. At 3, U3 is the displacement, F3 is the force. Now F2 value is also given. They have given the F2 value is also given, that is 200 kilonewton. They have given F2 as 200 kilonewton. Now we have to analyze this problem. So if you will see this problem, then you can correlate this problem with the derivation of stiffness matrix from the last video. In the last video, we have derived something stiffness matrix for such type of case where I have taken one side as fixed, another was free. But in this, they have given both sides free. That is the boundary condition. That is nothing, the boundary condition. But we have derived the stiffness matrix for such cases when there is sudden change in area, stepped bar. I have given the third case number 3, the stiffness matrix for a stepped bar. So see here, what type of bar element is there? Stepped bar, because here in the first element the area thickness is more, and coming to second element thickness is being reduced, means stepped down, right? So a stepped bar element. So how will you approach for such type of problem? So first we will calculate the stiffness matrix, right? First, what is our first step? Our first step is to calculate the stiffness matrix, because in this case each and everything is given. Like area is given, Young's modulus is given, everything is given. Suppose if they will not give the area, then they will give the, see here length is given as well as they will give the thickness also. Suppose here length is given 300 mm. Similarly, they will give the thickness also, so that you can find the area. But here in this case, area is directly given, and most of the cases they will give area directly, right? So first thing, what we need to calculate the stiffness of element 1 and stiffness of element 2 individually, and then we will find the global stiffness matrix. Why we need to find the global stiffness matrix? In the previous lecture already we have discussed global stiffness matrix is nothing, the matrix stiffness matrix for the whole system, whole element. And individual stiffness matrix, that is also called as local stiffness matrix, that we will calculate for individual element. So here there are two elements, element 1 and element 2. So we will calculate K1 and K2, and then finally we will find the stiffness matrix, that will be global stiffness matrix, by using this K1 and K2 value. Okay, so let's start. For element 1, what will be the value of K1? Already we have discussed K1 stiffness matrix, stiffness formula. If you will see K1, what will be the formula? If you remember, I have derived F is equal to K into delta, where K is what? AE upon L. So for element 1, what will be that? AE. So A1 E1 upon L1. A1 is your 2400 mm square. E1 is given 70 into 10 to the power 3 Newton per mm square upon L1. L1 is given 300 mm, right? So everything is given. Now, if you will calculate this value, we are going to get this value as 56 into 10 to the power 4 Newton per mm. This mm square will cancel out. This will become Newton per mm. Similarly, if you will calculate K2, this is for element number 1. This is for, let me write here, for element 1, K1. And now I am going to calculate for element number 2. So for element 2, K2 value we are going to find out. So K2 will be here A2 E2 upon L2. Again, put all these value. A2 value is given, E2 value is given, L2 value is given. So after putting all these values, or let me put here again 600 into 200 into 10 to the power 3 divided by 400. That will get this value as 30 into 10 to the power 4 Newton per mm. Now we have calculated K1 and K2. As we have calculated K1 and K2, our problem is almost solved. Why? Because we know these values. Now only what we need to do, we need to find the global stiffness matrix, right? So let me write the global stiffness matrix now. What will be the global stiffness matrix? K matrix. Already we have derived that K matrix. What will be the value of K matrix? That K matrix, if you will see in the previous lecture itself, we have derived that will be equal to K1 minus K1 0, then again minus K1. Here it will be K1 plus K2 minus K2. Here it will be 0 minus K2 and then K2. This is your global stiffness matrix, right? This will be your global stiffness matrix. So what we need to do now? Only we need to put these values of K1 and K2. That's it. We are going to get the global stiffness matrix. Same we will do here. So if we'll put these values, K1 value, what is your K1 value? See, 56 into 10 to the power 4. What is your K2 value? 30 into 10 to the power 4. So here you can see there is a common term, that is 10 to the power 4. So can we take this 10 to the power 4 outside? Obviously we can take, right? So let us take that 10 to the power 4 outside. Then see what we are going to get. 10 to the power 4 outside. Then K1. K1 is what? 56 into 10 to the power 4. So K1 will be left now 56. Then minus 56. Then 0. The next again minus K1. That will be minus 56. K1 plus K2. That will be 56 plus K2 is 30 into 10 to the power 4. So 56 plus 30. K2 minus 30. Again 0 minus 30 and here 30. Right? So this we got as our global stiffness matrix. Next, what we need to find? We need to find delta matrix. Delta matrix is what? Global displacement vector. So what will be the global displacement vector? You can see here how many nodes are there? 3 nodes. So how many global displacements will be there? There will be 3 displacement, that is U1, U2, U3. U1 will be at node 1, U2 will be at node 2 and U3 will be at node number 3. So we can write this delta will be our U1, U2, U3. Now next, that is our load vector, right? So F matrix. How many forces are there? Again same, F1, F2, F3. 3 nodes, 3 forces. Same as your displacement vector. So F1, F2 and F3. That's it. We got this. matrices. Now we need to find the unknowns. How will you find the unknowns? Because we know kf is equal to k into delta. So F matrix will be, now if you will write in the matrix form, F matrix will be K matrix into delta matrix. Just we need to write all, we have to arrange all these matrices in this form, F is equal to K into delta. Because in the previous lecture, if you will see the derivation, whatever we have derived, the stiffness matrices and the relation, again we establish the relation between force, displacement and stiffness matrix. What we are getting? We are getting F is equal to K into delta. This is the main formula, right? Whatever be the matrix, but the final result we are going to get is F is equal to K into delta. So here F matrix is nothing, F1, F2, F3. K matrix is 56 minus 56, obviously 10 to the power 4 is outside common. 0 minus 56, 56 plus 30, it will be 86, minus 30, 0, minus 30 and 30. And delta matrix is U1, U2 and U3. So we are going to put all these values together to get the required unknowns. So we can write it in this form, F1. Now F2, if you will see, I have given the value of F2. In the question itself, the value of F2 is given, that is 200 kilonewton. So everything we have taken in Newton, see here, everything we have taken in Newton, so also we have to convert it into Newton. So we can write 200 into 10 to the power 3 Newton, right? So we can convert this in this form. So F1 in place of F2, directly we can write 200 into 10 to the power 3. And then again, F3 is unknown. Then K matrix 10 to the power 4 outside. K matrix already we have developed the K matrix minus 56. Then it is 56. Sorry. We have already developed 56 minus 56, right? 56, this is minus 56, 0. Then again minus 56, then 86, minus 30. Then here again 0, minus 30 and then 30 into displacements. Displacement is U1, U2 and U3. Now we got this equation. Now what we need to see? We need to see the boundary condition. We need to see the boundary condition. Whatever the boundary condition is given in the question, or they will write, they will provide the details of the boundary condition. If they are giving at a particular point or particular node, the displacement is 0, they will write in the question itself, or else in the diagram, from the diagram, if anything is fixed, we can derive this boundary condition. So if you will see the problem, boundary condition means at first node, if you will see, this is fixed. If it is fixed, it means U1 value will be going to be 0. If something is fixed, then obviously this will not allow any movement, means displacement at this node will be 0. Similarly, if you will see at third, it is again fixed. So what will happen? Again, U3 will become 0. So let us keep this U1 and U3 as 0. So let us keep U1 value 0 and U3 value 0. Now, if you remember what I have said, if any displacement is 0, then that row we have to eliminate. So what we are going to do here, we are going to, U1 is 0, so we are going to eliminate this row. We are going to eliminate this row. As U3 is 0, we are going to eliminate this row. Okay. Now that is the about row. Regarding column, what I said, if U1, because this is the column of U1, this is the column for U2, and this is the column for U3. So if U1 is 0, we need to remove these columns also. This will become 0. Null and void, means there is no use of this, because U1 value will be 0. You can check it by multiplying also. If you will do each and everything, you are going to get that final result only. But if you will go for the standard method, then what you will do, again f1 into this will be equal to 0. You will make that much of equations, and finally you are going to get this equation what I will derive from here, right? So doing that much is waste of time. In this subject you have to apply this concept to remove the zero, or to remove the rows and columns based on the displacement value. If displacement is 0 at any node, just remove that column, and with the number of displacement, like if it is at second node, so second column you have to remove from stiffness matrix. If it is at node number 1, u1 is 0, then you have to remove the first column of the stiffness matrix. So u1 is also 0 as well as u3 is also 0. So which one is the column for u3? Third one. Remove this. Now what is left here? On the right, this side you are having 200 into 10 to the power 3. Then here 10 to the power 4 is outside, right? Next here left one is 86. And here leftover is u2. So directly from here, your unknown u2 displacement at the second node, you are going to get a displacement at the second node, and this u2 value you are going to get it as 0.233 mm. Directly we got the u2 value, right? So displacement we know. Now what are the unknowns? Each and everything we can calculate. For us, unknown is f1, f3 and u2, because u1 is equal to u3 is equal to 0, and f2 value is already given in the question. So for us, out of 6, what are the unknowns? f1 is unknown, f3 is unknown, and u2 is unknown. u2 already we have calculated. Now we need to calculate f1. So how will you calculate f1? Same thing, u2 value, keep it here in the matrix, same matrix, in this matrix only. In this matrix only, what we need to do, we need to keep this u2 value. So what we can write for f1? For f1, if you want to write the equation, so how will you write the equation for f1? From here, f1 will be equal to, see, f1 will be equal to 56 into 0, that will be 0, minus 56 into u2, so minus 56 into u2, again 0 into 0 is 0 only, so directly you will get f1 is nothing, minus 56 into u2 means minus 56 times u2 value already we have calculated, that is 0.233, right? Yeah, and 10 to the power 4 is outside here, so we have to consider this 10 to the power 4 also, right? 10 to the power is common, right? So it will be multiplied with this minus 56 into 10 to the power 4. So finally we are going to get this f1 value as minus 130 kilonewton. Just calculation, simple calculation is there. Once you will calculate, you are going to get f1 value as minus 130 kilonewton. Similarly, how will you calculate this f3 value? Same method. f3 will be equal to 0 into 0, 0, minus 30 into u2. So minus 30 into u2 into 10 to the power 4 is common, so 10 to the power 4, and remaining again 30 into 0, that will be 0 only. So once you will keep this u2 value, you are going to get f3 is minus 70 kilonewton. So whatever the unknowns was there, we have already calculated that unknown, right? So this will be the thing, whatever the unknowns are there in the question, we have just found that unknowns like forces and displacements. Apart from this, they can ask you stress values. Calculate the stress as node number 1, calculate stresses at node number 2, calculate stresses at node number 3. So what we have calculated till here is direct things, right? Now they can ask the indirect things, means they can ask the something which will be dependent on these values, like stress value, strain value. If you want to calculate a stress, Young's modulus is given. So what we need to find? If we find a strain, then we will be able to calculate stresses, because stress is nothing, strain into displacement. Sorry, strain into Young's modulus. right? So next, we are going to calculate stress. So before going to calculate the stress, let us calculate a strain also. We will see how to calculate a strain as well as how to calculate stress at for element number 1 and for element number 2. So for element 1, for element number 1, we are going to calculate strain first. So E1 will be equal to, what is E1? Now here you have to remember one formula, that is du by dx in element number 1, that is a strain displacement relation. E is equal to du by dx, a strain displacement relation that we have discussed in the first unit. From there, just you have to remember this formula. E is equal to du by dx, rate of change of displacement, nothing, strain, right? So E is equal to du by dx. Now here du, if you will see how we can write this du and dx. See, dx is nothing, length is that original length, upon original length only. Du, how you can write this du? Du we can write it as, because displacement, if you will see here in the problem, in first element, this is 1, this is 2. So here displacement you can see at node 2, the displacement is 2, and here node 1 is 1. So initial displacement 1, and then here it is no, at node number 2 u2. So we can write u2 minus u1 upon L1. L1 is nothing, 300 mm. So here directly we can write u2 minus u1 upon L1. So u2 value already we have calculated. U2 value is 0.233. U1 value fixed, so 0 upon L1. L1 is 300 mm. So we are going to get this value as 0.000776. Strain. What will be the unit of strain? This is dimensionless. Why dimensionless? Because strain is nothing, ratio. Ratio of what? Change in length upon original length. So there will be no unit. So strain E1 is nothing, 0.000776. So from here we can calculate stress also. Sigma 1. How will you calculate sigma 1? It will be equal to E1 into epsilon 1. From Hooke's law. Nothing I am using the new thing. Whatever we are discussing and whatever the formula I am using, that is either from your strength of material or already we have discussed that formula. So sigma is equal to E into epsilon. So from here sigma 1 value we have to calculate. E1 value already given in the question. See, E1 value is given here 70 into 10 to the power 3, and epsilon 1 already we have calculated. So just put it here, 70 into 10 to the power 3 into 0.000776. So we are going to get this value as 54.4 Newton per mm square. If we are getting positive, then obviously it is, they can ask the nature also. What is the nature of that stress? So what will be the nature? Either tensile or compression. So if we are getting value as positive, then it will be tensile. If we are getting the value as negative, then it will be compressive. So just you have to consider this signs: positive, tensile, negative, compressive. So here we are getting tensile one. Now for element number 2. For element 2, same way we will calculate it. Now epsilon 2, that will be again du by dx. For what? Element number 2. So for element number 2, what will happen? That will be u3 minus u2. Final one, because element number 2, so u2, here it is u3. So u3 minus, see here, u3 minus u2. So u3 minus u2 upon L2, u3 is 0, u2 value is already we have calculated 0.233 upon L2. L2 value is given as 400 mm. So we are going to get this E2 value as 0.000582. Now this value will be in negative, right? Negative. Remember this value is in negative. Why? 0 minus something will be in minus only. Why I have not written negative? Because for a strain, if it is negative or positive, that doesn't matter. Negative means the length is reduced. Positive means length has increased. But it will impact on stress value. Stress is equal to E2 into epsilon 2. E2 value is given in the question. Already it is given 200 into 10 to the power 3 into epsilon 2 value. Here we will take minus 0.000582. So we are going to get this value as minus 116.5 Newton per mm square. And here, since it is minus, so the nature will be compressive, right? So this stress is, so for element in element number 2, the stress developed is in of having which nature? Compressive nature. And in element number 1, the stress developed having tensile nature. That is the problem. That is the maximum thing they can ask in this bar element problem. They can ask the unknowns like displacements at the nodes. They can ask you to find the value of force, like they will give P, and they will ask you to calculate the value of P, right? So that is also we have calculated F1, F2. Nodal displacement already we have calculated U2. Then apart from this, they can ask elements, calculate the stress and strain in element 1, stress and strain in element number 2. That's it. That is the maximum reach of this problem. Maximum they can ask this much only, right? So just you need to practice more and more sums on the same concept. You will be able to solve all types of problems. Yeah. Apart from this, what they can do, one more thing they can do, they will ask this much only, but what they can do, they will change this shape. We have to convert that given shape into this type of shapes. So how will you do that? I will give you then some idea. Same problem they can ask in other way also. So let's see what way they can ask this problem. Now they have given this way, right? So here the problem is this is varying, right? This is not a linear, this is varying. So there will be a problem in calculating area, and they will not give the area. What they will do, they will give thickness, length, and whatever the thing is there. Suppose they have given thickness here at this end is 80 mm, and here the thickness they have given as, suppose, let us suppose 40 mm. I'm not going with the correct data, just for an example, let us see. And suppose at this point they have given a force is acting P force. So they are asking you to calculate this P force, and this length they have given from here to here. The length they have given is 300 mm. Suppose they have given a length of 300. At this point, they have given a load P. Now the problem is, at this point, if they have given the load, if we will go back to our basics, we have to take a node at that point. Means we have to divide this structure into 2 elements, right? Because if you want to find this force, then we need to take, so if we will take here, so let us take, this is node number 1, this is node number 2, and this is node number 3. Now we need to find the area of this. Area we need, because why we need area? Without area, how will you calculate stiffness for element 1 and the stiffness for element 2? Without length, how will you calculate a stiffness? So we have to transform this structure into a structure like this. The structure we have just solved same way. We need to convert this structure into this type of structure so that it will be easy for us to analyze this problem, right? So how will you convert? If you know how to convert, then remaining steps are as it is. then nothing is going to change. Only the thing you have to learn here, how to convert this type of structure into a structure that can be analyzed easily. So conversion we will see. So for this, what we need to do, and suppose they will give thickness also, because for this type of thing, if you want to calculate area, the thickness obviously they will give. Let us take the thickness they have given as 10 mm. So what we will do now? We will do one thing now. Area we will calculate at the nodes. So we have selected the nodes. Node 1 will be here, node 3 will be here. That is for sure, because that is the end condition. And a load is acting at the center. So obviously we have to select a node at that point also. So that is node number 2. 3 nodes we have selected. So let us calculate the area at the node 1, node 2, and node 3. So let us calculate the area. Suppose A1. How will you calculate area? See, thickness, this length is given 80 mm. They have given 80 mm at node number 1, right? So at node number 1, length is given 18. At thickness they have given is 10 mm. So how will you calculate that area? Width into thickness, that is 80 into 10. That will be equal to 800 mm square. Now, at node number 2, we don't know the thickness. At node number 2, we don't know thickness. Thickness is not 10 mm, but we don't know the width, whether it is 60, because it will vary from 80 to 40. Then obviously this will be in between 80 to 40 only, but the actual value we don't know. So let us directly jump to A3 first. So A3 here, the value is 40. Thickness given 10 mm, so that is 400. So what we are going to do now, we are just taking the average at that section. We are taking some assumption that whatever the average we are going to take, that will be the area at the node number 2. Almost it will be correct only, right? So average of A1 and A3 will give you A2. Just we are going to take the average. So average of 800 plus 400, 800, 400 divided by 2. How will you get that average? That will be 800 plus 400 divided by 2. That is equal to 600 mm square. So we have considered this is halfway. So the average became, that is 600. So we have A1 now, we have A3, and we have A2. Now coming to this section, right? Coming to this section, here we need to calculate this A1, and here we need to calculate A2. Because this A1 is nothing, area of element. Now this is element 1, right? Element 1, and this is your element number 2. So element number 1 is area 1, element number 2 will be area 2. So area 1. How will you calculate this A1? So A1 will be, see here, this is your node number 1. See this node 1, this is node 2, this is node number 3. So A1 will be nothing. At node 1, what is the area? 800. So 800. Plus at node number 2, what is the area? What is the area at node 2? 600. So 600 divided by 2 means average of these two. So average of these two, if you will do, we are going to get this as 700 mm square. Similarly, that A2 will be, what will be the area at second node? That is 600. What is the area at third node? Third node is 400 divided by 2. That is equal to 500 mm square. That's it. Now this problem is converted into this problem. We have A1, we have A2. Right? So we have A1 as well as we have A2 also. Now you will ask, sir, how to calculate thicknesses and length? If you want to calculate length, what will you do? Length. Just once think about this length. Area we have calculated. What will be this length? From here to here, what will be the length? This length is nothing half, because we are taking average. Average, if we are taking, means we are considering this section at the center. So if it is 300 mm, so this L1 will be 150 mm and L2 will be 150 mm. That's it. So we have converted this problem into conventional problem. Whatever the conventional problem we are going to solve that is easy for analysis, this typical problem is now converted into conventional problem. And now you can see this problem is equivalent to the problem that we have discussed. I think you won't get any problem while solving this. You won't get even doubt, because the next thing what we are going to do is completely same. Nothing is going to change now, right? Each and everything will be same now. Again, A1 value you know, L1 value you know, E1, E2 they will give, obviously they will give, or else in such cases, what will happen, your E1 value will be equal to E2, because what they will do, they will give the whole material is of steel or whole material is of aluminum. Then again, Young's modulus is going to be same. So for element 1 and element 2, Young's modulus is going to be same, only area is changed. Even length is also same, 150 mm and 150 mm, only area is changed. So from here we will calculate K1, K2, then we will develop the matrix, then boundary condition, then unknown forces, and whatever the problem, in the problem they will ask, you can solve that. So this is all about the problem related to bar element. I hope you will be able to do the problems. So just one suggestion, go through the video. If you are not able to understand, repeat it. And after completing this, take some problems from other sources and try to solve that. Okay. So thank you. We'll discuss the next in the next video.